In this presentation, we have to talk about beta function. We know that the beta function is beta of m comma n equal to integral limit varying from 0 to 1 x power m minus 1 into 1 minus x power n minus 1 into dx. This is our beta function. Now we may prove that beta of m comma n is equal to beta of n comma m. Prove that problem number 1, beta of m comma n which is equal to beta of n comma m. For that, take our beta function beta of m comma n which is equal to integral limit varying from 0 to 1 x power m minus 1 into 1 minus x power n minus 1 into dx. Consider this is equation number 1. This is our beta function. Here put x equal to 1 minus x. Just replace x by means of 1 minus x. Automatically the value of dx equal to, if you differentiate this, you can get minus dx. If you put x by means of 1 minus x, then dx should be replaced by minus dx. Then what about the limits? Lower limit is 0, so instead of x you have to put 0 for limits. We have taken x equal to 1 minus x. Here put x equal to 0 to get our lower limit, then x equal to 1. So the lower limit is changed as 1, and put the value of upper limit here is 1, x equal to 1, then x equal to 1 minus x, so 1 minus 1 equal to 0. This is our upper limit. If you replace x by means of 1 minus x, the limits are changed from 0 to 1 to 1 to 0. Now, if you substitute all these things in the above equation 1, we can get beta of m comma n is equal to integral limit varying from 1 to 0. Instead of this x, you have to put 1 minus x. 1 minus x power m minus 1. Then 1 minus x is our x. X power n minus 1. Instead of this dx, we have to put minus dx. Now, to change this negative sign, once again change the limits, which is equal to 0 to 1, 1 minus x power m minus 1, x power n minus 1 into dx. This can be interchanged as limit, integral limit varying from 0 to 1. Write down the term x power n minus 1 first, then 1 minus x power m minus 1 into dx. This is our beta of n comma m, because n term comes first. In the case of beta of m comma n, m term comes first, x power m minus 1 into 1 minus x power n minus 1. See here, this is x power n minus 1 into 1 minus x power m minus 1. Therefore, this is our beta of n comma m. We have taken beta of m comma n. We have arrived beta of n comma m. Therefore, beta of m comma n is equal to beta of n comma m. Consider this problem. Prove that beta of m comma n equal to integral limit varying from 0 to infinity y power m minus 1 divided by 1 plus y power m plus n into dy. For that, consider our beta function. Beta of m comma n, which is equal to integral limit varying from 0 to 1 x power m minus 1 into 1 minus x power n minus 1 into dx. Here put x equal to y divided by 1 plus y. Instead of x, we have to write y divided by 1 plus y. Then what about the value of 1 minus x? 1 minus x, which is equal to 1 minus of y divided by 1 plus y, which is equal to cross multiply 1 plus y minus y whole divided by 1 plus y, which is equal to 1 divided by 1 plus y. The value of 1 minus x is 1 divided by 1 plus y. Next, find out the value of dx. X equal to y divided by 1 plus y. Then dx equal to, consider this term, both numerator and denominator are having y terms. Therefore, you have to follow u by v formula. Dx equal to 1 plus y whole square. Write down the term as such in the numerator, 1 plus y. Differentiate this numerator, that is dy, minus of this y. Then differentiation of this 1 plus y. 1 plus y is dy, which is equal to, see here, 1 into dy plus y into dy minus y into dy whole divided by 1 plus y whole square, which is equal to dy divided by 1 plus y whole square. This is the value of dx. Now you know the value of x, 1 minus x and dx. How do we change the limit? Here, if you express the function in terms of x, the limits are 0 and 1. Now we are representing x in terms of y, so that the limits are to be changed. For that, we have to find out the value of y. We know that one minus x, which is equal to 1 divided by 1 plus y. Therefore, 1 plus y, which is equal to 1 divided by 1 minus x. This 1 plus y equal to 1 divided by 1 minus x. Then y equal to 1 divided by 1 minus x minus 1, which is equal to 1 minus, cross multiply this 1 minus x whole divided by 1 minus x, which is equal to x divided by 1 minus x. The value of y equal to, x by 1 minus x. Now come to our limit part. In the case of x, the lower limit is 0, upper limit is 1. So for lower limit, put x equal to 0. If x equal to 0, y equal to 0 divided by 1 minus 0. That means 0 by 1. 0 by anything, 0. So the lower limit is 0. This is lower limit. For upper limit, put x equal to 1. Here the upper limit is 1. If x equal to 1, then the value of y equal to 1 divided by 1 minus 1. Put x equal to 1. That is equal to 1 by 0. Anything by 0, infinity. So this is our upper limit. Lower limit is 1. While lower limit is 0, upper limit is infinity. If you substitute x by means of y divided by 1 plus y, 1 minus x in terms of 1 divided by 1 plus y, dx in terms of dy divided by 1 plus y whole square, the limits are changed from 0 to 1 to 0 to infinity. Now substitute all these values, write down the beta of m comma n. Beta of m comma n, which is equal to integral limit varying from 0 to infinity. What about the value of x? X equal to y divided by 1 plus y. Y divided by 1 plus y whole power m minus 1. Then the value of 1 minus x is 1 divided by 1 plus y. Here 1 minus x power n minus 1. Therefore, the value of 1 minus x is 1 divided by 1 plus y. 1 divided by 1 plus y power n minus 1. See here, 1 minus x power n minus 1. The value of 1 minus x is 1 divided by 1 plus y. Therefore, 1 divided by 1 plus y power n minus 1. Then the value of dy. Substitute the value of dx. Dx is, where is dx? Here. Dx equal to dy divided by 1 plus y whole square. Here. Dy divided by 1 plus y whole square. Now combine all these terms. This is equal to limit varying from 0 to infinity y power m minus 1 whole divided by 1 plus y power m minus 1 into 1 divided by 1 plus y power n minus 1 into 1 divided by 1 plus y whole square into dy. Just I have taken this as 1 divided by 1 plus y square into dy. Now align all these terms. This is equal to integral limit varying from 0 to infinity y power m minus 1 whole divided by 1 plus y power m minus 1 plus this term plus this term. You have to apply a power m into a power n rule. A power m into a power n equal to a power m plus n. So all are in terms of 1 plus y. Just add the powers. M minus 1 plus n minus 1. That is m plus n minus 2 plus 2. Therefore, this is 1 plus y power m plus n. Entire is multiplied by dy. This is the value of beta of m comma n. This is another one form of beta function. We know that beta function is beta of m comma n is integral limit varying from 0 to 1 x power m minus 1 into 1 minus x power n minus 1 into dx. But we can express beta of m comma n in this form also. This is another one form of beta of m comma n. In the same manner, we can prove beta of m comma n, which is equal to integral limit varying from 0 to infinity x power n minus 1 whole divided by 1 plus x power n plus m, both are same, m plus n, n plus m, into dx. This is also beta of m comma n. Yes, we have expressed beta of m comma n in terms of x. This is in terms of y. Now third proof. Prove that bit of m comma n equal to gamma of m whole divided by gamma of m plus n. You know the gamma function. Here gamma of n, which is equal to integral limit varying from 0 to infinity here, e power minus x power n minus 1 into dx. This is called gamma function, gamma of n, e power minus x power n minus 1 into dx. This is our gamma function. Now replace x by lambda y, which means x equal to lambda y. Substitute the value of x as lambda y. If x equal to lambda y, dx equal to lambda into dy. Now substitute these values in equation 1. Gamma of n, which is equal to limit varying from 0 to infinity, e power minus lambda y. Instead of x, we have substituted minus lambda y, just minus into this lambda y. Then x power n minus 1, which is lambda y power n minus 1. Dx is lambda into dy. Now this equation is modified as integral limit varying from 0 to infinity, e power minus lambda y, lambda power n minus 1, y power n minus 1 into lambda dy. Now we have to add the lambda terms. 0 to infinity, e power minus lambda y. See this lambda power n minus 1, this is lambda power 1. If you sum up these two terms, you can get lambda power n, because lambda power n minus 1, see here, lambda power n minus 1 into lambda power 1, which is equal to lambda power n minus 1 plus 1, which is lambda power n. Just a simple addition. This is lambda power n. You should understand this term clearly. Lambda power n. Then y power n minus 1 into dy. This is the value of lambda n. Consider this is equation 2. Say this is equation 1. Now in the same manner we can write gamma of m, which is equal to limit varying from 0 to infinity, e power minus lambda into x, then lambda power m, x power m minus 1 into dx. Say this is equation number 3. We have proved gamma of n equal to this much. Instead of n, if you introduce m, y should be replaced by x, and then n should be replaced by m. This is the value of gamma of n. Now multiply both sides of equation 3 by e power lambda. We know that we are expecting the term gamma of n here. Already we have expressed the term in terms of e power minus lambda x. Therefore, multiply both sides of equation 3 by e power minus lambda, lambda power n minus 1, and then integrate with respect to lambda. See here, gamma m, just multiply by e power minus lambda, lambda power n minus 1 into d lambda. Just we have to integrate. Limit varying from 0 to infinity. Just we have to express in terms of lambda n. This is our lambda n. E power minus lambda, lambda power n minus 1 d lambda is our lambda n. Multiply this side also. 0 to infinity, e power minus lambda, lambda power n minus 1 into d lambda into the same term. Limit varying from 0 to infinity, e power minus lambda x, lambda power m, x power m minus 1 into dx. E power minus lambda, lambda power n minus 1 multiplication should be remembered. Just we have to introduce gamma of n here, so that we have multiplied both sides by e power minus lambda, lambda power n minus 1, because gamma of n is e power minus lambda, lambda power n minus 1 into d lambda. Then this is say this term is our gamma of n, e power minus lambda, lambda power n minus 1 d lambda is gamma of n. E power minus x, x power n minus 1 into dx is also gamma of n. Just we have replaced x by means of lambda. This is our gamma of n. Now come to our right hand side, just align the terms. 0 to infinity, e power minus lambda, e power minus lambda x. Take this minus lambda outside. You can write 1 plus x. Just I have aligned these two terms. E power minus lambda into e power minus lambda x. Just we have to sum up these two terms. Take out minus lambda outside. So 1 plus x. Then lambda power m plus n minus 1. Just combine these two terms. Lambda power n minus 1 into lambda power m. Lambda power m plus n minus 1 into d lambda. Then x power m minus 1 into dx. Limit varying from 0 to infinity. Remaining terms, x power m minus 1 dx. Just I have written this one as a separate integral. Say this is equation number 4. Here put lambda into 1 plus x equal to y. Therefore lambda equal to y divided by 1 plus x. Then d lambda equal to dy by 1 plus x. Instead of this term lambda into 1 plus x, I have introduced a new term y. So lambda into 1 plus x equal to y. Therefore lambda equal to y divided by 1 plus x. Then d lambda equal to dy divided by 1 plus x. Substitute all these values in equation 4. Gamma of m, gamma of n, which is equal to integral limit varying from 0 to infinity. This is e power minus y, because lambda into 1 plus x is y. Then lambda power m plus n minus 1. This is the value of lambda. That is y power m plus n minus 1 whole divided by 1 plus x power m plus n minus 1. Instead of this lambda, I have substituted y divided by 1 plus x. That means y power m plus n minus 1 divided by 1 plus x power m plus n minus 1. Then d lambda. The value of d lambda is dy divided by 1 plus x. Then come to our second integral, limit varying from 0 to infinity x power m minus 1 into dx. Now come to this side, 0 to infinity. See this e power minus y power m plus n minus 1 into dy. Write this one as a separate term. Integral limit varying from 0 to infinity. These are all multiplication, so that we have to take this term to the second integral. X power m minus 1 whole divided by, align these two terms, this is 1 plus x power 1. This is 1 plus x power m plus n minus 1. If you multiply these two terms, just we have to add the powers. 1 plus x to the power m plus n minus 1 plus 1, that is equal to m plus n. Just I have used the rule a power n into a power n equal to a power m plus n. Entire is multiplied by dx. See this is our gamma of m plus n, because gamma of m is e power, see this gamma of n, general form, gamma of once again I am going to write this. You know that gamma of n is integral limit varying from 0 to infinity e power minus x power n minus 1 into dx. This is gamma of n, or gamma of n in terms of lambda also we can write integral limit varying from 0 to infinity e power minus lambda power n minus 1 into d lambda. This is also gamma of n. So e power minus y power m plus n minus 1 into dy. This is our gamma of m plus n. If I write gamma of m or n, we can say e power minus lambda power n minus 1 into d lambda. But here y power m plus 1 minus 1 term is present. So this is our gamma of m plus n. Then we may write gamma of m into gamma of n, which is equal to gamma of m plus n. Then this term, already we have proved this, beta of m comma n. Beta of m comma n. Now the above equation, provide some number to this. This is equation 5. Left hand side is gamma of m, gamma of n. So this e power minus y power m plus n minus 1, which means that this is gamma of m plus n. If you write gamma of n, that is e power minus x power n minus 1. The function minus 1. Here the function is m plus n. So that we have write y power m plus n minus 1. So this is replaced by gamma of m plus n. From this we can write beta of m comma n equal to gamma m gamma n whole divided by gamma of m plus n.